Okay. Hello, everyone. I hope you are doing well, and we start. Mhm. Do you see my screen?
Yes.
Thank you. Okay. Today's lecture is going to be about the arbitrage theorem, but first I would like to remind you a brief overview of option pricing, because you remember that the great main of our course to model the dynamic of the financial market. And it means that we are going to model riskless asset, risky asset, and the price of derivative. Often it is option pricing. So the list you can see is first the one period binomial model, and you remember that it was on the previous lecture. The arbitrage theorem, it's for today, and after that it is the multi-period binomial model, replicating strategies in this multi-period binomial model, American option, Black-Scholes formula, and dynamic delta hedging. Okay, it is like our road, what we are going to do in the future. Okay, so today the arbitrage theorem, and we start with the question what is betting, and let me explain it in terms of example. For example, you might say to your fellow train passenger, I'll wager $10 that we won't get to Chicago on time. You understand that to wager or to bet is the act of playing in the hope of winning. And in my example, the guys A and B wager that they would get to Chicago on time, but the passenger C and D wager that the train will manage get to Chicago on time. Understand? Yes, the situation. So the passenger A put $10, B $20, C $15, and D $10. So the total sum is how much?
55.
Yes, $55. Okay. And you understand that can be at least two situations if this train manage get to Chicago on time and won't get to Chicago on time. Yes. So so we're going to the next slide. Yes, and we would like to understand how this passenger can divide the money which they win, and what is the return function. So we can consider this experiment with the two outcomes. It is omega-1 and omega-2, and to compute the return function. Return function in this case means it is how much they can get money on the 1 unit of on the $1, in fact. So the total sum is 55, and the passenger A and B put $10 and $20. So it means that the return function will be 1.83 if their wage coincide with the outcome of experiment. And otherwise, they lost the money, and the return function equals -1. You can see the similar situation for the next return function, because it is just two return function, because you remember that will be two bets, one on time and one otherwise. Okay, so if will be the outcome that the train manage get on time, the passenger R get 10 multiplied this return function, it's 18.3, and passenger B get 20 multiplied 1, 83, it will be 36 and 7, and the total sum is $55. Yes, it's easy. For the second scenario, the passenger C and D win, but A and B lose. So we can compute the sum of what the passenger and D get. Yes, it is similar to the first scenario. So now you have you know what is the return function. You see that it is R up 1 and R up 2, and this is a scenario which and G is 1 and 2, 2. So if it is coincide, yes, so it is the unit of your win. Okay, so in general case, we can consider the experiment which have m possible outcomes, and its probability space, and suppose that exactly n wagers concerning this experiment are available. So you see that m and n are different number. So we can have m possible outcomes, but formulate only n wagers, only n. No, and n can be more and less than m. Okay, and in general case, the return function for a unit bet on wage I are, and you can see how we can write the return function. Return function looks like this, and maybe okay. And now about a betting strategy. A betting strategy, it's like portfolio. Betting strategy is simply a collection of bets. It is like amount involved in game on different wages. It is, you remember, like on the previous lecture, we considered the portfolio, and it is like the vector or collection, and every coordinate means the number of different assets, if we consider the derivative. But in this case, it is the number of of different bets. Number means amount of monies. Yes. Okay. And now we can compute the wealth of portfolio. So we just need to multiply it how much we invest and what is the return function of the 1 unit. And after that, to sum all this. In mathematics, it calls the sum of products. Do you know?
Scalar product.
Yes, you're right. Okay. Okay. What is the problem? Let's consider an experiment with a set of possible outcomes, and we have m outcomes. G equals 1, 2, 3, m. And the probability vector is q, so it is about scenario. It's about scenario. Maybe it is not the file. It is the previous file, because you see that the probability vector and number of scenario, it can be different, m and n. So I corrected, but maybe now I opened not this exactly file. Okay. Suppose that n wagers, so maybe we need to correct in this case n wagers concerning this experiment are available. Equation is in follow. Is there a betting strategy that always results in a positive win? So what does it mean? If we, for example, for the example above, the one or more passenger can bet no one wager, but several. For example, the passenger A can bet that can wager $10 that train will get in time, and for example 20 that no, about the opposite situation. Understand? What does mean the portfolio, or what does mean? Okay. What does mean the portfolio or a betting scheme? Yes, so it's not we put our money on the one bet, but on several bet. Okay.
Yep.
No.
Yes, we understand.
Yes. Okay. Thank you. And this problem was solved by Arrow and Debris, and what is interesting that they were awarded the Nobel Memorial Prize, Arrow in 1972, Debris in 1983, for the work on developing the theory of complete markets and applying it to the problem of general equilibrium. And the arbitrage theorem, it is about like equilibrium. And this theorem states that exactly one of the following is true. Either there exists a probability vector Q1, Q2, and QM. It's previous my version. For any wage, or else there exists a bidding scheme that leads to a sure win. So for any scenario, okay, again, or there exists a probability vector, and it doesn't matter what wage we choose for any wage. The mathematical expectation per your function regarding this probability vector is 0. Or there exists a bidding scheme, like portfolio, that leads to a sure win. Okay, and we would like to prove this theorem. So for this, we need to remind what is a primal and its dual linear programs. Do you remember this from the Modo, for example? Yes? Modo. No? Do you remember? Do you remember about a primal linear program? What is this? Yes? No, for example,
I think I remember, yeah. I was solving it. Yeah.
For example, we have the task 2x1 plus 3x2 max and subject to the system, and its system, it is inequality, for example, 5x x1 5x1 plus 7x2 less than 1, minus x1 plus 2x2 less than 5, and 2x1 minus 6x2 less than 4. Okay, it is this, it is like this, and subject to this linear system. And now we need to write the dual linear program. And notice, please, that we don't have the condition that all these x are not negative or positive. We don't have this. Okay. So please, can you write the dual program? What will be this function? It's called subject function. We need to take b. We need first what we need. We need to find how much y to input and find how much. What do you think for this example? How much will be y in the dual linear program? Do you remember? If you don't remember, so please, it is similar. It is in general case, but I ask you to write not in general, but in this concrete case. Eva, can you say? Eva, are you here?
Yeah, I'm here, but no.
No, how much? Why in this case in dual linear program if we know everything about primal linear program? We have M in linear program. Have? Okay, Rosa, what are you thinking? Rosa.
Sorry, I just joined. I had some problems with internet. I didn't hear the question.
I understand. You would like that I ask? I repeat the question.
Yes, if
Yes? Okay. Okay. Um, you see on this slide a primal and its dual linear program in general case. Yes? I would like to write this primal and dual linear program for the, like example. So a primal linear program will be this. So you see that it is subject function, but this it's my subject function. For example, yes. So you see what is C1, C2, yes. You see this linear system, and you see what is A and what is B, yes. And please, I would like that we write, and I ask you how I can write the dual linear program. And first, I need to write how much y I need. Do I need? What is m? What is m?
I guess M is like the amount of
Okay, okay. So say what I need to write that I would like to find y1. I'm waiting.
and Y2, I guess.
Y2.
And Y3.
Yes, and Y3. Yes. And Danila, I saw your hand. Thank you. So 3. Why? Because it is how much linear equation inequalities we have in the primal program. Yes, 3. Okay. So how I can write the subject function?
It would be one Y1.
Yes, 1 multiplied 1 yes, because b it is this vector. Yes, this vector, it's vector b. Okay, so plus
5Y2
plus 5y2
and plus 4Y3
and plus 4y3. Okay, and I need to write that I would like maximize or minimize this function.
minimize.
Minimize, thank you. Minimize. And what is about this system of linear inequalities?
We must first vector multiply for y1, second vector for y2, and third vector.
Okay. Okay. Please say this. I need to write.
Okay, so 5 y1 minus y2 plus 2y3.
Okay. Plus 2, okay. y3, yes, because really we take all this coefficient, yes, and multiplied by this vector of y's or y's,
Yeah.
and it equals C1. What is C1?
C1, it's over 2. It's
Yes, yes,
yeah,
yes,
here.
really, it's C1 and it's C2. C2. So it is 2, and the next,
It's 7 y1
mm-hmm,
plus 2 y2
mm-hmm,
and minus 6 y3
mm-hmm, equals
equals 3.
equals 3. Thank you. Thank you. And in this case, I need to write that y1, y2, and y3 not negative, yes? Not negative. Okay. Okay. We repeat it, yes? Uh-huh. And we know the duality theorem of linear programming. It is for the model subject. For the subject. And this theorem states that if a primal and its dual linear program are both feasible, then they both have optimal solution. And the max value of the primal is the minimum value of the dual. So in our example, if we solve it the primal and we find that the maximum value, for example, is 24, so it is for the dual program, it's the minimum value 24, okay? Yes? And
Yes.
but if either problem is infeasible, then the other doesn't have the optimal solution. Doesn't have the optimal solution. Okay? Okay? And now we can see that a consequence of the dual theorem is our arbitrage theorem. Okay. Okay, so for the proving, assume that theta up n plus 1, no, it is denote, yes, denote, be a sure win for the gambler. And what we would like, if it is sure win, if is it a sure win, yes, we would like that it will be maximum, yes, sure win, sure. It will be maximum. And consider the betting strategy, theta 1, theta 2, theta n. It is how much money involved in first bet, in the second bet, in the n bet. Okay? So it's our subject function, maximum, and subject to. What is this? It is like unit. It is a return function. We multiplied by how much money involved in this unit function, and similar for the each bets. And all this sum of these products is called the wealth of portfolio or the wealth of betting strategy. Yes? And we would like that this sum will be more than the sure win. This sure win. Yes? Sure win. Okay. So I hope that you can write this like system, and after that, what we need, we would like to move this to the right side, so it will be with minus, okay? And after that, we would like denote minus reg like aeg, but an plus 1g like 1 and this like xe. It is because we would like to write like in general case dual and primary and dual problems. Okay, so what it will be if I would like to write this in new notes. It will be it is this reg with minus, but this with minus we denote just like eg. So it will be a 1 1 it is this, it is a eg eg and theta it is like, you see, like x e. So it will be a11 x1 plus a12 x2 plus point and plus maybe sorry, maybe I would like
Sorry, сейчас подожди.
okay, maybe I write this, maybe this. So it is 1 admit 1 a11 x1 plus when y2 x2 plus the next it will be a1 n xn it is this sum, yes, but you see that we have else theta n plus 1 and theta n plus 1 it will be in our the new notations it will be x n plus 1, yes, x n plus 1, and all this less than 0. It's okay, yes? Is it clear? Guys, the first.
Yep.
Clear, okay. So the first, and we have m. So the last will be a m1 x1 plus a mn xn and plus x n plus 1 less than 0. So it's okay. And now we would like to construct the dual linear program. Do you remember what will be the subject function? First, what is our new variables? Y. How much Y we have? How much Y we have? It will be in this case. How much? It is
2.
no 2. How much?
M.
M, yes, thank you. So for dual linear program, we need to input y1, y2, and ym. After that, I would like to write the subject function. Do you remember how we can write subject function? Mhm. You remember subject function? If, oh, well, no, this, sorry. Oh, subject function. It is like B, this coefficient we multiplied by Y. So in our case, what it will be?
It will be 0.
Yes, all coefficient is 0. Yes. So we need to multiply this vector by this vector. It is like scalar product, it's inner product for this, and it will be 0. Y1 multiplied 0, 0, just 0. Just 0. Or I can write, no, 0 multiplied y sub y is 0 and 0 minimum. Okay, so it's easy. But what is this system for the dual linear program? What do we need? Do you remember? Danilo,
Yep, we should.
right? Or multiplied, maybe you would like to say. We should multiply what?
Mhm.
No,
A,
all this. Yes.
yes,
So I can write A
1
1 multiplied
by Y1.
Y1. Okay. Plus.
And etc. like A N M A1 N.
You're right. MN YM, and it equals
0.
0. Yes, you're right. And it equals 0. Okay. Admit. After that,
Why AMN? Isn't it supposed to be AM1?
it is A11 multiplied y Y1. It's clear. Yes.
Yeah.
The second A21, and the last A MN, because this M1, yes, M1. Okay, it's my bad. Thank you. M1, yes. Okay, after that, etc. And about this, we can write. It's easy. Yes, it is Danilo. A.
No, it's
A.
like
It's
A1
M1. It's
N.
Y1 plus.
Oh, M1 yeah, plus
Yes.
A.
At this MN, yes, MN YM, and equals 0 again, yes.
Yes.
Yes, y0, because in this linear function, it is all coefficient theta with 0. Yes, we don't have. So theta 1, we don't have, it means that it is 0 multiplied theta 1 plus 0 multiplied theta 2 plus 0 multiplied theta n, yes, and just theta n plus 1 have the coefficient 1, yes. So it means, and for the last column, what we have right?
That's our
Mhm.
yj,
Yes,
yj, okay, or yj is
no, yes, it's 1 multiplied y1, yes, plus, and the last will be ym and equals,
1.
yes, and equals this one, yes, really, thank you. Yes, well done. So we have this dual linear program, linear program, and how we'll see that we can consider this variables vector y1 and ym like probabilities vector, because because you remember, and we need to write that all y g more than 0, yes, 1 1, so on, and 1m, all this more than 0, non-negative. So it is like probability vector, all coordinate is not negative, and the sum of this equals 1. And if all this task is feasible, so it will be really dual, it will be minimum, but the primary task has maximum, so it is sure win will be maximum. Yes. Okay, so so you can see all that we write on the previous slide, like a primary linear program, xn plus 1 maximum, and subject to this system of linear inequalities. And dual linear program, it is 0 minimum. It is like on the previous page, yes, subject to this. Yes. And after that, we can consider y1 and so on, ym as a probability vector, because sum equals sum of this y is 0, and every coordinate is more than 0. And this dual problem will be feasible, and its minimum value will be 0 if and only if there is a probability vector under which all wagers have an expected return of 0. And if the dual is infeasible, then there is no solution to the primal. But this implies, yes, that 0 isn't the optimal solution. Yes, like minimum isn't the optimal solution, and thus there is a betting scheme whose minimal return is positive. So there is a sure win. Yes, it is in fact arbitrage theorem. Okay, so the proving of this arbitrage theorem is not difficult. We need just to write the primary and dual task, and to remember that first we input theta n plus 1 like sure win, and we would like that it will be maximum and subject that the for any for any betting it will be more than sure win. Okay, and we can consider this on the practice example. Maybe you know about sport betting and its activity of prediction sports result and placing a wager on the outcome. Yes, you know about this, guys.
Yep.
Yes,
Yes, I know.
yes. So now sport betting is very popular, and we can do it online. And the example, okay, the example, it will be on the Euro this year, and it will be the Spain France. You see the date, and will be the three wagers. Yes, 1, X, and 2. And it's this coefficient. It's like returns. Okay, so we would like to apply arbitrage theorem. For the first outputs, the coefficient, it's called odds, 2.75. And we would like to compute risk neutral probabilities, because okay, this first R1 equals 2.75 if it's win, and -1 opposite. Yes, so 1e, if e equals 1, it will be 2.75, and if e doesn't equal 1, it will be -1. Yes, for example, if we put $10, so for you lost is $10. Okay, so we would like to compute risk neutral probabilities, and you remember what is this? Yes. So what does mean risk neutral probability? For example, this with probability Q1 and this 1 minus Q1 minus Q1. Risk neutral probability means that the mathematical expectation, what is mathematical expectation? Rosa.
Sum of outcomes multiplied by their probability. Probabilities.
Please repeat.
Sum of outcomes multiplied by their probabilities.
Yeah, probability. Okay, it's clear, but equals what it equals. Sum of products equals. So 2.75 multiplies Q1 plus minus, yes, -1 multiplies 1 minus Q1. Okay, it's mathematical expectation, yes? All of this, it's mathematical expectation. But risk neutral, what does mean? That mathematical expectation equals how much?
0?
0, yes, thank you. 0. So we need to solve this. It will be 0.75 Q1, okay, там Q1 minus 1 and plus Q1, yes, and plus Q1 equals 0. So, so it will be like Q1 plus 275 Q, and in the bracket 1 plus 2.75 and equals
1? No?
yes, yeah, thank you, and equals 1. So this Q1 equals this one divided by 1 plus 2.75. 1 plus 2.75. Okay. So we have 1 divided by 1 plus 275, and it will be 0.27. It's Q1. And similar, we can compute risk neutral probability for this outcome. Yes, and it's similar. 1 plus 2.8, it is Q2. And this Q3. Okay. So according to the arbitrage theorem, we need to check if this sum equals 0 or equals 1 or not. So sum of this Q, it will be 0.27 plus 0 point this plus and it will be less than 0, yes? Okay? Do you agree? Guys, do you agree? Danilo.
Yeah, we agree.
Okay, thank you. Okay, thank you. So, let's repeat. What is about this theorem? Betting strategy, the problem, the theorem. Exactly one of the following is true. Either there exists probability vector for which Q it is like risk neutral probability, but in our case there exists probability vector. In our example, we find Q1, Q2, and Q3 for which mathematical expectation equals 0, yes, but is Q1 and Q2, Q3, is this a probability vector? In our example, what do you say? Danilo,
Maybe yes.
why? What is probability vector? It is vector with coordinates which are not negative, and the sum of coordinates equals 1. But in our
okay.
case, not. Yes, not.
Yeah.
So it's not true. It's not true. So this true. This true that there exists a betting scheme that leads to a sure win. So it is for any scenario, the wealth of betting strategy is positive, not negative, negative, but positive, exactly positive. Yes. Okay. So in our example, You see that this probability, this vector isn't probability vector. So there is a betting scheme that we have the wells more than zero for every scenario. First, for example, first scenario, it is like one is true. One outputs is true. If one outputs is true and we involve theta one money, so we win, yes?
Yes.
But for the second scenario, if it's true, so the money which were involved in the second bet and the third bet, we lost, yes?
Yes.
But we state that it's more than zero. The next scenario that this outputs is true, but this and this no. So this we lose, but we win only on this wage. And then next, sorry, and the last outputs, it is this, and all our bet for the first and the first outcome isn't true, so we lost this money. Lost this money. After that, we can solve this system of linear equation, and it will be like set. No, yes, set in space. Set in the space. Do you understand? No, for example, using Wolfram. Yes, what is the set? But I didn't eat. Okay, and for this solution, for the set of solution, for this space of solution, I put 1 point. Put one point. Do you understand about this? No? Rosa? Yes. Yes. Okay. So one of the solution is this point with coordinate 2, 2, and 2. Let's check it. Let's check that it is really solution of this system of linear equalities. We substitute 2 instead of theta 1, and it will be 2 multiplied to this plus substitute 2 instead of theta 2 and 2 instead of theta 3. And it will be 1.0. It is more than 0, more. After that, we substitute again theta 1, theta 2, theta 3 in this inequality. It is more than 0, and in this inequality, it is more than 0, and you can check it by yourself. Okay. What does it mean? It means that if we put your money like bet 2 on the first outcome, bet 2 on the second outcome, and bet 2 on the third outcome, so in any cases, for any scenario, we can that for your function will be positive, more than 0. It is like, no, yes, positive for use for the betting portfolio for all scenarios. But what can you say about this result? If we are thinking like a gambler, like really, how much money did you have to make to make these wagers?
We had $6, for example.
$6. $6. Okay, but our win is or this or this or this. Yes, for all scenarios we don't lose, but our win is less than how much we put. Yes. So it is arbitrage theorem. It is not like for mathematician, maybe it is good, but for sport gambling, maybe isn't good, this theorem. Yes, maybe for managers of this sport games, sport betting. Sorry. Okay. So that's all. So today you studied about betting strategy, what is odds, what's the return function, what is the arbitrage theorem, and we can apply all this. For example, you can read about this in these handbooks, and for example, Sheldon and Ross, it is page 72 and 84. And now now we can open the test, and it will be the exercise from this book. From this book. Now I'm going to show you this. So it is so we have lecture 5, arbitrage theorem, and we have the test, and you have 3 equations, 3 problems. Create any linear program and construct its dual program. And please take, you remember that in the lecture I get the subject function for 2 variables x1 and x2, but you please take other number of variables, for example, x1, x2, x3, or x1, x2, x3, x4, yes, and construct a dual program. After that, exercise 6.4 from this handbook Ross, I will show you and explain why we don't use arbitrage theorem for our profit. Maybe you already explained, but please write this. So exercise 6.4, 6.4, it is, you can find this handbook on this to do, and 6.4, 6.4, maybe. What is the page? Page after that. After that. Mhm. Oh, the arbitrage theorem. You can write this about this return function. It is example, yes, how to compute risk neutral probability. It's a different example. And you can read about proof of the arbitrage theorem and exercise. You can find there 6.1, 6.2, 6.3, 6.4. For example, this with solution. Okay.
Okay.
Okay. So thank you for your attention. Maybe I can end recording.